Hi guys, welcome to yet another chemistry video. Today we will be exploring valence bond theory in even more depth. We will be covering sigma bonds, pi bonds, and even delta bonds. We will also be exploring hybridization in more depth. First, let's cover a bit more on the shape of orbitals. Recall that we can describe atomic orbitals as wave functions. Constructive and destructive interference are two ways waves combine when they overlap. Constructive interference occurs when waves are in phase. Crest meets crest, trough meets trough, causing their amplitude to add up and create a wave with a larger amplitude. Destructive interference occurs when waves are out of phase. Crest meets trough, causing their amplitudes to cancel each other out, resulting in a wave with a smaller amplitude or zero amplitude. When atomic orbitals combine, they create asymmetrical atomic hybrid orbitals with one large lobe and one small lobe. The large lobe is present because of constructive wave interference, and the small lobe is present because of destructive wave interference. The amount of asymmetry increases as small orbitals combine and as small p and d orbitals are involved. Now, let's go through the different types of hybridizations with relevant examples. Let's start with sp hybridization. The process of sp hybridization allows for the formation of two equivalent bonds in a molecule of BeCl2. Let's look at the ground state electron configuration of Be. As you can see, Be is unable to form any bonds. All electrons are paired, but covalent bonding depends on having at least one unpaired electron that can overlap with an orbital from a partner atom. Thus, Be promotes one of its 2s electrons into the 2p orbital and changes into a hybrid state with two vacant sp orbitals, which now allows it to form two bonds. This is favored as energy released in the formation of the two bonds can compensate for the energy needed to promote an electron from a 2s to a 2p orbital. In sp2 hybridization, one ns orbital and two np orbitals are mixed to produce three equivalent sp2 orbitals. The three equivalent sp2 orbitals contribute to three electron domains. Hence, the hybrid orbitals are directed towards the corners of a trigonal planar shape. As an example, let's look at a molecule of Bf3. The process of sp2 hybridization allows for the formation of three equivalent bonds in a molecule of Bf3. This is favored as energy released in the formation of the three bonds can compensate for energy needed to promote an electron from 2s to 2p orbital. Lastly, let's look at sp3 hybridization with the C in methane, CH4, as an example. In sp3 hybridization, one ns orbitals and three np orbitals are mixed to produce four equivalent sp3 orbitals. The four equivalent sp3 orbitals contribute to four electron domains. Hence, the hybrid orbitals are directed towards the corner of a tetrahedral shape. The process of sp3 hybridization allows for the formation of the four equivalent bonds in a molecule of CH4. This is favored as energy released in the formation of the four bonds can compensate for energy needed to promote an electron from 2s to 2p orbital. There are three ways in which orbitals can overlap to form covalent bonds. Sigma bonds are head-on overlaps of orbitals. Pi bonds are side-on overlaps of orbitals. Delta bonds are side-on overlap of 2d orbitals in such a way that the combined electron density has four alternating lobes of opposite phase around the internuclear axis. Okay, let's explore sigma bonds first. A sigma bond is formed via the head-on overlap of simple atomic and/or hybridized orbitals. This overlap results in maximum high electron density along the internuclear axis with maximum electron density along the internuclear axis. Now, let's look at pi bonds. A pi bond is formed via the side-on overlap of unhybridized p or d orbitals. This results in a high electron density above and below the internuclear axis with zero electron density along the internuclear axis itself. In chemistry, a delta bond is a covalent chemical bond in which 4 lobes of an atomic orbital or one atom overlap 4 lobes of an atomic orbital on another atom. This overlap leads to the formation of a bonding molecular orbital with 2 nodal planes which contain the internuclear axes and go through both atoms. A bit more info on sigma and pi bonds is that a sigma bond always forms first in any chemical bond formation. In multiple bonds, the pi bond forms only after the sigma bond is established. Head-on overlap yields a stronger bond due to more effective orbital overlap, while side-on overlap produces a weaker bond due to reduced orbital overlap. Hope you better understood valence bond theory from this video. Thank you for watching.